Severnbroen, der åbnede i 1966, og hvis design revolutionerede den måde, man byggede hængebroer på.
Majestic, dramatic, awe-inspiring. These are the bridges that are worldwide icons, as well as engineering marvels.
She's beautiful.
Each of them broke new ground. The first, the biggest, the longest, and the tallest.
I'm Rob Bell, an engineer, and I'm on a global adventure to discover how and why these magnificent structures were built, and to learn about the sweat and the sacrifice that went into their construction. Oh, hey!
I'm going to take you closer than ever before.
Oh, this is magnificent.
Inspect them from every conceivable angle.
Oh, yeah.
And meet the men and women who keep them working round the clock, no matter what.
Check this out!
These are the world's greatest bridges. This is the Severn, the longest river in Britain. It's also a daunting natural obstacle. One that firmly separated England and South Wales for centuries.
Then, in 1966, this appeared.
The Severn Bridge. It's virtually a mile long, 446 feet high, and with a central span of 3,240 feet. Built from over 18,500 tons of steel, it took 3.5 years to construct and cost £8 million. Nothing out of the ordinary about the price, but the design, that was something else. From the day it opened, it's won admiration for its sleek and streamlined shape. But it wasn't designed like this purely for aesthetic reasons.
The story of this bridge is the story of our battle to overcome the raw forces of nature.
The English and Welsh have been crossing the Severn since Roman times in boats. The first serious proposal to connect their two countries by bridge didn't come about until 1824. But most of these plans were dismissed as unworkable. And that's because the Severn estuary presented a string of obstacles for any potential bridge builder.
Some of the problems they were wrestling with were the sheer length of the span required to cross to the other side, the notorious weather conditions, and the fact that this was one of the most important shipping lanes in Britain. No plans were ever going to be approved if there was even a potential hazard to navigation. So that's why this, the first road bridge crossing, wasn't completed for another 142 years after it was first proposed.
But there had been a different type of bridge across the estuary. By the mid-1800s, railway mania had swept the country. In one 4-year period, there were 10,000 Acts of Parliament giving permission for new lengths of track. When it came to moving passengers and freight, this new means of travel eclipsed all others.
No wonder then that the first bridge across the Severn would be a railway bridge. And it was built right here, nearly 11 miles upstream from where the road bridge is located. And today, these stone towers are all that remain of it. And that's because the Severn Railway Bridge was ill-fated, almost from the very start.
Deep in the vaults of the Institution of Civil Engineers in London are photographs of the bridge under construction.
These photos really are fantastic. This one here with the bridge almost completed. It was a conventional single-line viaduct here, made up of 6,800 tons of iron. In length, this was over 4,000 feet long, and there were 21 spans in total, being held up 70 feet above the water. And this bridge took 4 years and 3 months to finish, and cost a total of £278,000, which in today's money is around 26 million. Here, we've got some photos of the workers out on site. But what these photos don't show are the fierce conditions they had to work in. Day and night, battling tide and fierce weather conditions.
The Severn Railway Bridge opened on the 17th of October 1879. But almost immediately, a serious flaw in its design came to light.
The reason many of the proposed Severn bridges never got off the ground was because they were considered too hazardous to shipping navigation. And yet, the railway bridge was approved, despite having 21 piers across the river.
That made collisions likely, and over the years, there were many.
The most serious of all came on Tuesday, the 25th of October, 1960. It was 10:30 p.m. and a thick fog descended on the Severn.
Two tankers, the Arkandale H and the Wasdale H, were making their way upriver, laden with volatile cargoes of black oil and petroleum spirit. Lost in the fog, the two vessels came together. And as their skippers tried desperately to separate them, they got swept along by the powerful tide.
A collision with the bridge was unavoidable. And as the Wasdale H slammed into one of the piers, iron girders rained down from the bridge above, piercing the tankers and igniting their fuel cargoes. The resulting explosion wrecked both ships and ripped apart two spans of the bridge.
As light dawned the next morning, the full scale of the disaster became clear.
5 crewmen from the Wasdale H were dead. The bridge was in ruins, and so were both tankers. Today, you can still see their rusting hulks at low tide behind me here. Silent, enduring monument to that disaster.
The bridge did not endure. In 1967, demolition work got underway, and the first Severn Bridge is now almost forgotten. But just 5 months after the disaster, construction of a new bridge began. A road bridge that would test its designers and builders to their limits. They'd witnessed the tragic mistakes of the past. The question was, would they learn from them? The Severn Bridge revolutionized the way that modern bridges are built. And that's because it was designed to not only conquer the elements, but to do what the earlier rail bridge hadn't. Allow shipping to pass through one of Britain's most important waterways unimpeded.
Despite the failure of the original railway bridge, the need to span the estuary had never gone away. And by the early 20th century, another mode of transport had begun to rival and even overtake the train: the motorcar.
The post-war period brought a huge expansion in Britain's road network. Tens of thousands of cars and lorries crisscrossed the country, transporting people and freight.
But this modern development underlined an ancient problem: how to travel the mile or so from Bristol across to Chepstow in South Wales without it taking an age.
To travel by road, you had to go via Gloucester, where tailbacks could stretch for hours. Otherwise, there was the ferry, which operated between Aust and Beachley.
But the ferry service was beset by problems. It couldn't run at high or low tide, didn't run at night or in bad weather. So actually, there were very few services running every day. On top of that, there were the queues to get on board boats like this. Often there'd be signs telling drivers they'd need to wait for 1 or 2 hours, or sometimes even more.
But by the early 1960s, an alternative was on its way. One that would close the ferry service forever.
A new bridge over the River Severn was finally being built.
Like the ferry, it would follow the route from Out to Beachley, and it would be a suspension bridge. But why this design?
In very simple terms, a bridge is a structure that holds up a deck over which traffic or pedestrians can travel to get from A to B. Now, the type of bridge that you build, i.e. the way that you choose to support that deck, is the biggest decision you've got to make. So, for example, I have here a model of a very simple viaduct. I've got my bridge deck here being supported by these multiple piers underneath. So, let's pop traffic on top. I need to load that down. This is a very heavily loaded truck. Let's pop a bit of freight on there. My truck can pass safely across. I've got a very stable bridge, but I've also created a problem. The river underneath here has a fair amount of shipping traffic, and with all my piers, I've increased dramatically the risk of some kind of collision. In fact, that's exactly the design problem that the Severn railway bridge suffered here. So, let's look at it another way. If I remove the piers underneath, let's get rid of these for now. I'm now left with my viaduct with just 2 piers. I've removed that risk of collision. My ships can easily and safely pass underneath, but I've created a problem. When I pop my traffic back on top, my heavily laden truck here, as it gets into the middle, you can see my bridge deck starts to sag in the middle. I've created an unstable bridge. And with more and more heavy traffic on top, it's a matter of time before the bridge fails completely. So let's look at another solution. Now, if I were to build 2 tall, strong towers on my remaining piers on each side, and then connect those at the top, and then all of these smaller cables from the top underneath the bridge deck below, what I've created is a suspension bridge. So let's test it out. Let's take our same heavily loaded truck and pass that across the bridge deck. Look at that. That is so well supported. You're no longer getting that sag. In fact, I can push down on top. Actually, I can push down quite heavily and it will still take the weight without sagging down. I can easily get my ship underneath. And that's why when you've got a span as wide as this that needs to be kept clear underneath, most of the time it's a suspension bridge that you'll find doing the job.
To design this suspension bridge, 2 large engineering firms were employed, each with their own area of responsibility. Mott, Hay and Anderson would be in charge of the substructure, the bridge's foundations, including the piers and the anchorages, whilst Freeman, Fox and Partners would be responsible for the superstructure, the steel towers, cables and the deck.
The challenges of constructing a bridge here across the Severn estuary would test both those companies to the limits of their ingenuity and their engineering prowess.
The first problem was how to construct the massive reinforced concrete piers that would support the bridge. This is never an easy task, but factor in the Severn estuary and it's as tough as they come.
That's because this river has the 2nd highest tidal range of any river anywhere in the world.
The difference between high and low tide in the Severn can be over 15 meters, with water flowing at speeds in excess of 9 miles an hour.
The tide's so powerful here, it creates a natural phenomenon called the bore, a large wave that's produced as the tidal waters are pushed up the narrowing channel of the river. And the Severn bore is one of the biggest in the world. So big, you can actually surf it.
The record for surfing the bore is held by this guy, Steve King. He rode it for over 9¼ miles. I'm not so sure if I'll make it that far.
That was absolutely amazing. It's such a cool feeling out there. I've just experienced one of this country's greatest natural phenomena, and it's so much fun. But for the guys building the Severn Bridge, that tide was anything but fun. At times, it must have just felt like a completely unsurmountable obstacle. It's so powerful.
Construction on the bridge's foundations started in May 1961 with the piers.
You can see the Orse Pier behind me, holding up the tower here on the east side. It's perched out on this rocky limestone outcrop called Ulverston Rock, which is only visible at low tide, like now.
Work could only be done at low tide, in windows as narrow as just 30 minutes. Within that window, the ground had to be prepared, concrete laid down, and men and equipment evacuated before the tide rushed back in.
And the site where the men were working would be completely submerged under more than 12 meters of water. And it would be another 6.5 hours before the next brief window of construction could commence. The work here, or down there, was all about precision timing. Get it wrong and the consequences would be disastrous.
And the construction of the second pier, at Beachley Head on the Welsh side of the river, presented even more significant obstacles. Located 200 meters offshore, there was no natural rock outcrop on which to construct the second pier. Instead, massive steel-lined pits were dug, allowing men and machines to work even at high tide, up to 25 meters below the water level. For the construction workers, these were truly challenging conditions.
This is the rock level. This is us continuing to dig down into the bedrock. One of the things about sheet piling is that it does tend to leak rather. And particularly as a ferry went past and caused waves, there'd be little spurts of water from all these little joints. We don't mind getting soaked. We're always out in the weather.
Part of the construction period for these foundations covered the winter of 1962, the particularly harsh winter. Did that make a difference to the work that went on here?
As far as the works in the river were concerned, there were large chunks of ice. You could call them icebergs, but they were, right up to where we're standing, they were ice flows. The foundations here were a major civil engineering success in a very hostile environment. And they are a rather unsung part of the marvellous Severn Bridge. We wouldn't have the top part without the bottom part.
In total, it took 2 years to construct the foundations for the Severn Bridge. But sadly, engineering in such hazardous conditions as this made fatalities extremely likely.
The first came on Sunday the 19th of November, 1961. It was late afternoon when 3 men working on the construction of the piers fell into the Severn and were quickly swept away on the rising tide.
As accidents like this were expected, rescue launches were on constant standby. With fading light and freezing conditions, time was of the essence. The rescue launch Isabella, crewed by Jack Hollins and John Newton, set out on a desperate search.
Unknown to them, a ferry, the Severn Princess, also heard the distress call and managed to pluck all 3 men from the freezing water. As night fell, there was a delay in getting the message to the rescue launch that the workers were safe.
By the time Isabella finally turned for home, 2 tanker barges, the Wisedale H and the Wharfdale H, were heading downriver towards her.
16-year-old Chris Witts was a deckhand on one of them.
Why were the 2 tankers heading along together?
We tied together because it meant that they only needed one skipper to steer both barges. But in actual fact, we were breaking company rules. And in all my time working on the river with those tankers, that was the only time we ever did it. And of course that night it all went wrong.
The rescue boat Isabella had sailed towards them, mistaking their navigation lights for distant traffic. The result? A fatal collision.
Suddenly there was this crashing noise and great shock when we went up on deck and looked over the bow. Between both bows was this starting to break up wreckage of a rescue launch with a man stood on the wreckage. We got a rope down to him and he hangs onto the rope and we pull him up quick. But as we're pulling him up, he's shouting to us that his mate is in the water. And there is this man in the water, arms in the air, head above the water, and he's slowly slipping down under. And he slipped under the water. End of him.
The crewman who lost his life that night was John Newton. His body was never recovered.
John Newton was one of 6 people who died during the construction of the Severn Bridge. Although a mercifully low number for an engineering project of this scale and complexity, 4 of them, including Newton, died in boat accidents, a testament to just how lethal these waters are.
And as construction continued and it was time to move the bridge's deck into place, those lethal waters would once again present the project with some of its greatest challenges. Most people get their first glimpse of the Severn Bridge from the ground, usually while driving along a motorway. But to appreciate it fully, I'm going to view it from the air.
From up here, you can see the Severn Bridge in all its glory. This giant, shining white structure, elegantly projecting itself out over the estuary below. It's such an impressive landmark, just stunning. And you can see that the Severn crossing is actually comprised of 4 separate bridges, making their way across this giant physical barrier of the estuary. You've got the Orse Viaduct leading into the Severn Suspension Bridge itself, going into the Beachley Viaduct, and then there's the wide bridge. It's just absolutely awesome from up here. But it's this one, the main structure itself, that's truly iconic. Because before it was built, suspension bridges just didn't look like that.
Instead, they looked like this. Massive structures crisscrossed with lattices of solid steel. The Severn Bridge is delicate by comparison. Its deck looks paper thin.
And that radical redesign was partly thanks to 2 things: the wing of an aircraft and an unfortunate accident.
The firm contracted to design the Severn Bridge superstructure was Freeman Fox and Partners. And the project was led by 2 of its senior engineers, Dr. Bill Brown and Sir Gilbert Roberts. Roberts was the senior of the 2 men, with vast experience and a reputation for being meticulous and methodical. Brown was 20 years younger, inventive, innovative, always looking for ways to push the engineering envelope.
During the mid-20th century, they worked together on some of the world's biggest bridge projects, with their differing styles complementing each other. And throughout the 60s, they could even have been described as the engineering world's Lennon and McCartney.
They won contracts to design 3 new suspension bridges in the UK, over the Humber, the Forth, and the Severn. The original plan was for this one to be built first, but then the government changed its mind, ordering work to begin on the Forth Road Bridge instead.
As it turned out, this delay proved rather fortunate.
Originally, the Severn Bridge was going to have a latticed, deep steel truss deck. This was supposed to help it withstand winds of more than 100 miles an hour. But when the model of that deck was tested in a wind tunnel, it broke free of its anchors and smashed to pieces. And as they only had 2 weeks to conduct these tests, there was no time to build another model.
Brown saw the accident as an opportunity. He was a man obsessed by aerodynamics, so much so he built this, his very own wind tunnel. And now he had an idea for a revolutionary new aerodynamic design for the decks of suspension bridges. The trouble was, Brown's ideas came at a time when people were nervous of change.
And that was understandable, as the last radical redesign of suspension bridge decks had ended in catastrophe. Opened in 1940, the Tacoma Narrows Bridge in Washington State sported a streamlined, slender deck reinforced by 8-foot-deep plate girders along its edges. But this deck bucked and swayed even in light winds, earning it the nickname Gallopin' Gertie. Only 4 months after opening, it was hit by sustained 40-mile-an-hour winds. The buckling intensified and the bridge tore itself apart.
Now I can use Bill Brown's wind tunnel here to demonstrate why Galloping Gertie's deck failed. So inside here, I have installed, ready to go, a model of Galloping Gertie's deck with its unaerodynamic plates down each side. So let's switch her on. We've got it set at just under 15 miles an hour, and you can see the bridge deck has started to wobble, started to oscillate slightly from side to side. And the longer you leave it, the bigger that oscillation becomes. Just look at it go now. And this is at the same wind speed, just under 15 miles an hour. As the wind passes around the bridge, it adds energy to those oscillations, into that flutter, until eventually the bridge just destroys itself. Which is why Brown came up with this, the aerodynamic box girder. And you can see it's got this streamlined shape to it. It's not at all dissimilar to the profile you get on an aeroplane wing. Apart from here, it's just turned upside down. Let's see how this one performs. So we've got the wind speed now up to around 85 miles an hour. So look at this, at this much higher wind speed, there's no flutter there whatsoever, unlike before. And what's going on here is actually some very clever aerodynamics. Because of the profile, because of the shape of the deck, as the wind passes across, the air underneath is moving faster than the air over the top. And because of that, the air pressure underneath is less than that on top. So what you get is this net effect of the air pushing down on the deck and forcing it into place. It's absolutely genius. Now, whilst there's no sign of that oscillation, that flutter, you can see that the deck is moving slightly in the wind. It's bobbing a little bit up and down. Now, there was never any concern that that would cause a catastrophic failure. But after Tacoma Narrows, there was a real anxiety about any kind of movement. And it was Brown's colleague, Sir Gilbert Roberts, who came up with a solution for that.
Up until this point, the hangers that link the deck to the main cable had been completely vertical on all suspension bridges. But Roberts realized that if they were inclined in an inverted V formation, they'd absorb this bobbing motion. With this one apparently simple change, the movement on the aerodynamic deck design was eliminated. Construction on the steel superstructure of the Severn Bridge could get underway. And the first parts built were the biggest.
These majestic steel towers, reaching 400 feet in height, are actually hollow boxes made from stiffened steel plates. And like so many elements here on the Severn Bridge, the design of these towers was something new. Because the new aerodynamic deck was so much lighter than traditional suspension bridge decks, that in turn
meant the towers could also be lighter.
Next, 18,000 miles of galvanized wire were spun back and forth across the estuary to create the two massive suspension cables. Finally, the bridge was ready for its deck.
The revolutionary deck sections were assembled here at the Fairfield shipyard in Chepstow. Now, the shipyard may long since have been abandoned, and this whole site in its final stages of demolition before a complete redevelopment. But back in 1965, this place would have been awash with workers, busily moving those streamlined shapes about before finally lining them up to be launched out into the water.
The construction of the Severn Bridge had already included some truly impressive feats of engineering. But perhaps the biggest was still to come.
With the aerodynamic sections fully assembled, it was time to get them out and up onto the bridge. But this would prove to be one of the riskiest and most difficult elements of the entire build.
Despite weighing 120 tons each, the hollow deck sections could float, allowing them to be sent out into the estuary and then lifted up into position. In theory, this sounded easy. But once again, this environment proved to be a formidable adversary.
The tide was such an obstacle. There were only about 10 days in every month where it was possible to float the sections out onto the estuary. In total, it took 18 months to get all 88 sections into place.
When the decks were finally in position, they were welded together. And this was another technique that helped to keep the Severn Bridge so lightweight. Early metal bridges tended to be riveted or bolted together. And in a structure containing hundreds of thousands of rivets, that's an awful lot of additional weight. Welding, on the other hand, gives you a strong join without adding extra weight. But it's a fiendishly difficult skill to master, as I'm about to learn.
Well, I've not done loads of arc welding, Steve, but I'm keen to have a go.
Yes. We've presented you with two typical beams of steel, but we're going to keep it very simple to give you a nice fillet weld joint there.
I appreciate
hopefully.
that. Thank you.
Electric arc welding creates an intense temperature that actually fuses the metal together.
And the ferocity of that arc is just phenomenal. Oh, I pulled away.
Right, well, I know what happened there. I pulled the electrode too far away from the metal here, which meant that I'd cut the circuit, and so the arc disappears. Yeah. That's not looking great, that, is it, so far, Steve?
Well,
You can be honest, I won't be hurt.
not too bad, except for a couple of gas holes, but not too bad at all. It takes years, and, you know, that's straight in at the deep end you've gone there.
I mean, you can see how difficult it is for a novice like me to get a decent weld here. But I'm doing it in this nice controlled environment of Steve's workshop here. The welding being done on the Severn Bridge, putting all the deck sections together, was at height in all sorts of weather with a killer estuary down beneath. I know where I'd rather be.
After 3.5 years and a cost of £8 million, the Severn Bridge was complete. On time and on budget. And it truly was, and it truly is, an engineering marvel, with its graceful, sleek lines stretching out across the estuary. And at the time of completion, it was the 7th longest bridge anywhere in the world, and it was by far the lightest.
The entire steel superstructure weighed just 18,500 tons. That's less than just one of the towers on the Golden Gate Bridge, which weighed 22,000 tons each. Both Sir Gilbert Roberts and Dr. Bill Brown won international praise for their revolutionary design.
But just 4 years after it opened, there were major disasters on 2 other bridges designed by the same men. And that put the safety of this one into serious doubt.
The Severn Bridge is a wonder of British engineering. When completed, it was the lightest suspension bridge in the world for its span and loading. And yet it's strong enough to withstand some of the fiercest natural forces in the UK. Its revolutionary aerodynamic deck design changed bridge building around the world. When the Queen officially opened the bridge on September the 8th, 1966, it caught the public imagination. It not only united England and South Wales by road for the very first time, its elegant and graceful design was viewed as another British triumph. Coming just 6 weeks after England's dramatic World Cup win, the opening tapped perfectly into a national mood of celebration. Even the Ouse to Beachley car ferry, which was put out of business the day the bridge opened, gave it a celebratory last pass by. The chief designers of the bridge, including Dr. Bill Brown and Sir Gilbert Roberts, both won worldwide praise for their work. But this mood of celebration and congratulation was to be short-lived. On the 2nd of June 1970, the Roberts and Brown designed Milford Haven Bridge in Wales collapsed during construction, killing 4 workers. Then, just 4 months later, the same thing happened with another of their bridges, and this time the consequences were even more devastating. The Westgate Bridge over the Yarra River in Melbourne, Australia, was 2 years into construction when a section of its deck failed without warning. Construction teams were working on and inside the deck when it fell. The 2,000-ton span came crashing down on the workers' huts below, instantly crushing those inside, and then the entire mass plummeted into the Yarra River in an explosion of gas and dirt and twisted metal. 35 people lost their lives as a result. Another 18 were injured in what was one of the deadliest bridge construction disasters of modern times. Both the Milford Haven and the Westgate collapses were due to failures in their box girder decks, and that put the stability of other box girder deck bridges into serious doubt, including the Severn Bridge here. Could its revolutionary aerodynamic deck also be at risk of sudden and catastrophic failure? An urgent investigation got underway, and it would soon provide the answer. What was discovered was that both the Milford Haven and the Westgate bridge decks were being constructed as cantilevers. Kind of like if I use this crude model here with my ruler on my 2 foundations, gradually, section by section, gets added onto the end, and your bridge deck extends outwards. Now, when my cantilever is quite short here, if there's any excessive weight or stress on the end, it's not so big a deal. But when it is at its longest, that same weight and load I put on the end, you can see causes a much greater stress in the structure. And that's exactly what happened with both the bridge collapses. The cantilevered decks were put under excessive stress at their most critical moment. And although the Severn Bridge behind me also has a box girder deck, the sections were raised into position and not cantilevered out. So it was never submitted to those stresses. Although the Severn Bridge was declared free from the risk of catastrophic deck failure, there was a separate safety issue looming.
This bridge had been designed to have a 120-year service life. But by the 1980s, barely a fifth of the way into that life, it was already showing serious signs of fatigue.
The problem? Overuse.
It had been designed to support a certain volume of traffic, known as its live load. But by the mid-80s, that volume was often double the maximum load the designers had allowed for.
Strengthening and reinforcements were put into place, but whatever work was undertaken, it couldn't solve the underlying problem.
the volume of traffic continued to increase, and congestion here became a regular issue at peak travel times.
Worse, although the bridge itself was designed to withstand the high winds that tear through the estuary, there was scant protection for the increasing number of cars and lorries upon it. This meant that the bridge often had to be closed in severe weather.
These closures and delays posed a threat to the economy of the whole region, an economy the bridge itself had helped to grow. There was only one thing for it: another crossing.
And this is it, the second Severn Bridge, located 3 miles downstream from the first one. Opened in 1996, it's almost 17,000 feet long, 449 feet high, and carries 6 lanes of the M4 motorway across the Severn estuary.
It's also the first bridge in the world to have its traffic protected from high winds by shielding.
This feature has meant that the road route between England and South Wales has managed to stay open even in truly atrocious weather, with the new bridge taking most of the strain and the original one carrying on in a state of semi-retirement.
But there's one controversy that's common to both. In order to pay for construction and the general upkeep, there are toll charges. But whilst it's free to drive into England, you have to pay to enter Wales. Here we go.
But now there's some good news.
The traffic here has exceeded expectations, and the money owed will soon be paid back. And once it is, both bridges will pass into public ownership, and the toll charges may well be scrapped.
It's hard to believe that it took until 1966 for a road bridge to appear across this estuary. Now there are 2, uniting England and Wales and boosting the economies of each.
The commuting masses might plump for the speed of the second Severn crossing, but I'd much rather take a little more time and travel across this iconic bridge. It is a remarkable piece of British engineering, and one that's conquered a hostile natural environment and inspired engineers all around the world to build bridges that are both strong and graceful.
Lige om lidt skal det handle om en af USA's mest populære præsidenter, John F. Kennedy. Vi fortæller om hans liv med deltagelsen i 2. verdenskrig, de mange hemmeligholdte sygdomme og ikke mindst ægteskabet med Jackie, som var med til at